So we have seen how integers, positive and negative values, are represented in a computer using the binary system. Now we are going to cover how real numbers are being represented. So what is a real number? Real number is a number that has a whole part and a fractional part. So 104.32, the 104 is the whole number and 32 is the fractional part. So positions to the left of the decimal point are the positions 10 to the 1, 10 to the 2, so it's the tens, the hundreds, the thousands, etc. And then positions to the right of the decimal point are the 10 minus 1, 10 minus 2, which are the fractional part. So how do we represent real numbers in a computer? Well, the same rules apply in the binary system as in the decimal system. That is, the decimal point is actually called the radix point, and the positions to the right of the radix point will be 2 to the minus 1, 2 to the minus 2, etc. And then positions to the left of the radix point will be 2 to the 1, 2 to the 2, etc., which will make up the number. Now, a real value in base 10 or decimal system can be defined by the following formula. So you have a sign, which is a plus or a minus, times the mantissa. The mantissa is all the digits that represent that number, times 10 to the exponent, which all it does is multiplies from some power of 10 that will make it move the decimal point. So the representation is called a floating point because the number of digits is fixed, that's the mantissa, but the radix point floats. So for instance, minus 120.01 in a floating point value will be represented by minus 12,001 times 10 to the minus 2, because we have actually moved the decimal point 2 places to the right. So that's 10 to the minus 2. Now a binary floating point will be a binary floating point value will be defined in a similar fashion. It will be the sign times the mantissa times 2 to some exponent to some power. So let's see how we will be converting a real number in the decimal system to the binary system. For instance, 20.25. So we divide the number into its whole part and its fractional part. First, we convert the whole part, which is 20, and as we have seen from the previous chapter on binary systems, that's equivalent to 10100, and we do that conversion by dividing it by 2 several times until we find the remainders. Then we need to convert the fractional part, which is 0.25, and the way to do it is by actually multiplying by 2 each time. So you take the 0.25, you multiply by 2, and it gives you 0.50. 0 is the significant digit. Then you take the rest of the number, 0.50, and you multiply by 2, and then you get 1.00. So at this point you end the multiplication because you don't have anything left. So 0.25 is equivalent to 0.01 in the binary system. So the number 20.25 is equivalent to 10100.01 in the binary system. Now, a form of floating point representation in which the decimal point is kept to the right of the leftmost digit, it's what it's called scientific notation. So for instance, this real number, we take the point, the decimal point, and we move it all the way to the first digit, or between the first and the second digit. In other words, between the 1 and the 2 in here. and then we have to count how many decimal places we have moved. So that's 1, 2, 3, 4. So this number, this real number, is equal to 1.2 and all these digits exponent plus 4 in scientific notation. Alright, so enough about numbers and real numbers and how they're represented in the computer system. Now let's go into how text is represented in a computer. So as you very well remember, computers are electronic devices. They use electricity and therefore they use the on-off state. And that's why they use the binary system, because it's the perfect system that represents the on-off state. So in a binary system, how would you represent a character? Well, there are a finite number of characters to represent in a language. So you just list them all and assign each one a binary string. So what is a character set? A list of characters and the codes used to represent each one. So you have a list of characters from the language and then their equivalent code to represent each one in a computer. Each code will be a binary string. Now, computer manufacturers used to have their own, every single computer had their own character set until they all agreed to standardize it, and they call it the ASCII, which stands for American Standard Code for Information Interchange. And then originally that ASCII character set used only 7 bits to represent each character, because the 8th bit was being used for some kind of check value for transmission or something like that. So it was only 7 bits that were used to represent each character, and therefore it only allowed us to represent 128 unique characters. Later on, then they modified the character set and they call it the extended ASCII, because they allowed all 8 bits, which meant that a total of 256 characters could be represented. This is the original ASCII character set that used only 7 bits to represent characters. As you can see, it's 0 through 12, that's 13 rows, and 0 through 9, that's 10 columns. Times 13, that's 130, minus 2 positions that were not used, that's 128. So these are the 128 characters represented in the original ASCII character set. Now the first 32 of them didn't have a character representation. They were used from some kind of special purpose. So for instance, the ASCII 10 was used for line feed, just feeding the next line, and then the character 13 was used for carriage return, so you could return back to the screen, to the first column of the screen, and so on and so forth. So each one of these had like a different purpose, but they didn't really have a character representing them. And then starting from this one all the way to the tilde, they all had a representation. So we can see that we have the capital letters in the alphabet, the lowercase letters, punctuation marks, etc., etc. So all of them had a unique character set. I mean, a character code. So the first 32 characters in the ASCII character chart do not have a simple character representation to print to the screen, because they were used for different purposes. Now, with the use of computers in other languages other than English, then make them necessary to use in international languages, like Russian and Thai and Chinese and all the other languages, which use a lot more than 256 characters. So the extended ASCII was not enough. So they came up with something called a Unicode. character set. And the Unicode character set, instead of using 8 bits per character, it started using 16 bits, which is equivalent to 2 bytes. So 2 to the 16, that meant that we could represent 65,536 characters. But still, the first 256 characters correspond. The first 256 characters in the Unicode character set correspond exactly to the 256 characters of the extended ASCII character set, just to make sure that there's no clashes. So examples of Unicode character sets, for instance, A, which is part of the English language, that's 410041. That's the 16-bit character code, and it's part of the 256, as you might very well have guessed. And then the Russian Cyrillic, this one, for instance, it's 042F, and this Chinese character, for instance, is 345F. So pretty much all the other characters in all the other languages could be represented using the Unicode character set. Now the problem is, if we assign 16 bits to each character in a document, then you start counting the amount of characters times the amount of words times the amount of paragraphs. So in a document, that 16 bits per character will use too much file space to store it. So we started thinking about we need ways to store and transmit text more efficiently and with minimal file space. So they came up with a lot of compression techniques, but these are the most common ones: keyword encoding, rung length encoding, and Huffman encoding, and we're going to cover them each one in detail. So the keyword encoding, for instance, what it does is it basically replaces frequently used words with a single character. So for instance, the word the is used a lot in the English language, and if we could just replace it with the tilde symbol, then we will be saving 1, 2, 3 minus 1, 2 characters. We'll be saving 2 characters for that word every time that word appears in the document. And for instance, the word these could be replaced with the pound symbol, so we will be saving 4 characters. So given this paragraph, for instance, we hold these truths to be self-evident that all men are created equal, blah blah blah, all that stuff. And then the encoded paragraph will look something like this. We hold pound, and pound, remember, it's the equivalent to these truths to be self-evident, and then $ is that all men are created equal, etc., etc. So what did we really save with doing this keyword encoding? The original paragraph, for instance, was 656 characters. The encoded paragraph turned out to be 596 characters, so we save a total of 60 characters, which gives us a compression ratio of 596 over 656, so it's 0.9. It's not the greatest thing, really. I mean, that compression ratio is not that good. So the question is, could we use this substitution character for all text? And the answer is no, because some texts use some of these codes, like $ and pound, and therefore they cannot be encoded. So that's one of the limitations with the keyword encoding. So next, the run length encoding. So basically you take a single character that may be repeated over and over again in a long sequence, and then you replace a repeated sequence with first a flag, second the repeated character, and then the number of repetitions. So for instance, the flag could be the asterisk, N will be the character repeated, and then 8 will be the number of times that character is repeated. So we could replace 8 ends, which will be 8 bytes, with just 3 bytes, asterisk n and 8. So if this is the original text, for instance, B, 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 J, 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 K, all that, the encoded text will be something like star, that's the flag, character B 8 times, 2, 4, 6, 8 times, and then J, J, J. Now why isn't the J encoded? Because it will take the same amount of space to encode the J, 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 or more space to encode the double L. So because basically it will be star J3, which takes the same amount of space as J, J, J. So it's only worth it when it's more than 3 or more, or 4 or more characters, I should say. So for instance, this original text, the original size is 25, the encoded text is 15, so that gives us a 0.6 compression ratio, which is pretty good. It's almost half, but it's pretty good. Now this type of repetition doesn't really occur in the English language. So what would be a situation in which it might be useful for? And the answer is in DNA encoding. In DNA encoding, you use a lot of the same characters, the RNA, whatever, molecules, proteins, and all that stuff. So there's a lot of repetition. So this encoding will save us a pretty good amount of space, around 0.6 compression ratio. Next one, the Huffman encoding. So the Huffman encoding says, why should the character X and Z, which they're very seldom used in the English language, take up the same number of bits as the E or the space, which are used a lot more? So Huffman codes uses variable length bit strings to represent each character. So the more the character is used in the language, the less amount of bits will be used to represent it. More frequently used letters have shorter strings to represent it. So for instance, A, it's a very commonly used character in the English language. It will be represented by the 00 Huffman code, and the E by 01, and the L by 100, etc. So for instance, the word ball board will be translated in the Huffman encoding by this long string. So basically you take the B, where's the B? Here's the B, it's a 1010, you put the 1010, then the A, here's the A, a 00, put the 00, etc., etc. So you come up with a total of 28 bits to represent the word ball board. Now, ball board has 9 characters times 8 bits per character. That will be a total of 72 bits needed without the Huffman encoding. But with the Huffman encoding, it would only take 28. So that gives us a compression ratio of 28 over 72, which is 0.38. That's a pretty good compression ratio. It's less than half. That's really good. In Huffman encoding, no character's bit string is the prefix of any other character bit string, as you might guess, because you don't want it to conflict. So, for instance, to decode a Huffman encoding, how would you do that? So you look for a match from left to right, bit by bit. Then you record the letter when a match is found. And then you begin where you left off, going from left to right until you decode the entire string. So for instance, if you were to decode this string, Huffman string, how would you do it? Well, you start with a 1 and you look, okay, it could be an E, an L, an O, an R, a B, or a D. Then you take the 0, so you're looking for a 1 0. 1 0 could be an L. These are discarded. 1 0 could be a B, and 1 0 could be a D. Then it's a 1. So 10, this one is discarded, so it could be either one of these two. 101, 101 could be a B or a D, and then 1, so it will be a D. 1011 is a D. Therefore, the first character is a D. And you keep going on until you decode the entire string. The technique for determining codes guarantees the prefix properties of the codes. So there are two types of codes. There's the general code and the specialized code. The general code is based on the use of the letters of the language that you want to encode. Whether it's English, Spanish, French, then the use of the letters will be different depending on the language. So that will determine what kind of codes will guarantee the prefix properties of the codes. And then in a specialized type of code, it will be when it's based on its text itself or on a specific type of text. Alright, so this gives us all the way to the end of the how to represent text and real numbers in a computer. And in the next video lecture I'm going to be covering how to represent audio and video.